Hello everyone. Welcome back to Dr. Liu's VCE Physics channel. Today, let's learn together about the 2025 physics examination. We will master the trickiest quantum mechanics and matter wave questions on the VCE Physics exam with a structured, step-by-step approach. In this video, we break down essential concepts, including wave-particle duality and quantization, and analyze real exam data showing where nearly half the cohort lost marks. Learn how to implement a powerful backward mapping strategy to navigate complex, multi-step calculations smoothly, and discover how to avoid common traps like the speed of light error, unit conversion penalties, M to NM, and incorrect transition diagram arrows. Perfect for students looking to move past simple formula plugging and secure full marks on high-scoring exam questions. Janet and Boris pass electrons and X-rays through the same crystal sample and observe that the diffraction patterns produced have a similar spacing, as shown below. This is because the electrons and X-rays used have similar. To determine why the diffraction patterns are similar, we can use a structured syllogistic approach often applied to VCE physics problems. Premise 1. The spacing and geometry of a diffraction pattern are determined by the ratio of the wavelength to the size of the gap, or crystal lattice spacing. Premise 2. In this photo, the prompt states that both the electrons and X-rays are passed through the same crystal sample. This means the lattice spacing is a constant for both experiments. Conclusion. Since the diffraction patterns have similar spacing, the wavelengths of the electrons and the X-rays must be approximately the same. Which one of the following phenomena can only be explained using the concept of quantization? This question asks students to identify the phenomenon that can only be explained by quantization. Using a structured syllogistic approach to evaluate the phenomena. Premise 1. Quantization refers to the concept that physical properties, such as energy, occur in discrete packets, or levels rather than a continuous range. Premise 2. Absorption spectra occur because electrons in an atom can only transition between specific, discrete energy levels. This requires the absorption of a photon with an energy exactly equal to the difference between those levels. This phenomenon cannot be explained by classical wave theory and relies entirely on quantized energy levels. Conclusion. Therefore, absorption spectra is the phenomenon that can only be explained using quantization. Why the other options are incorrect. B. Diffraction patterns observed with electrons. This demonstrates the wave-like nature, wave-particle duality, of matter rather than quantization specifically. C. Interference patterns in Young's double-slit experiment. This is a classic demonstration of wave behavior, and was historically used to support the wave model of light before quantum theory was established. D. Increase in photocurrent with intensity. While the photoelectric effect as a whole supports the particle-photon model, the specific observation that more light intensity leads to more current, given the frequency is above the threshold, is actually consistent with classical wave theory. More energy in the wave would be expected to liberate more electrons. The quantum part of the photoelectric effect is the existence of a threshold frequency and the independence of maximum kinetic energy from intensity. Diffraction patterns can be produced by directing electrons at a graphite foil. Electrons are emitted by a hot filament at the cathode, accelerated by the anode and hit the target graphite foil, producing diffraction patterns on a fluorescent screen, as shown in Figure 18. To find the accelerating voltage, we work backward from the final goal. First, we recognize that the voltage is determined by the kinetic energy the electron gains. To get that energy, we need the electron's speed, which can be derived from its de Broglie wavelength. The key to starting the problem is the highlighting rule. Since the diffraction patterns are identical, the electrons must share the same wavelength as the X-rays. By following this logic, from wavelength to speed, then to energy, and finally to voltage, we can solve the problem step by step. The statistics from this question, where 49% of the cohort received 0 marks, reveal several critical areas where students struggled. The speed of light trap. Many students incorrectly used light speed, c, to calculate the electron's energy. It is vital to remember that while X-rays travel at the speed of light, electrons are massive particles and move much slower in this context. The velocity dead end. A significant number of students successfully calculated the electron's velocity, but were unable to progress to the final answer. They lacked the logical bridge to connect velocity to kinetic energy, and ultimately, to the accelerating voltage. Math versus physics. Many attempted to solve this using simple mathematics, plugging numbers into a single formula, rather than treating it as a multi-step physics problem. Lack of a meaningful start. Nearly half the students either left the question blank or failed to identify the first step, recognizing that the same diffraction pattern implies identical wavelengths for both the X-rays and electrons. Student recommendation. To improve performance, students should move away from memorizing isolated formulas and instead practice detailed, multi-step problems. This question tests the dual nature of light, as both a particle and a wave. First, we treat the photon as a particle and use Planck's equation to find its frequency based on its energy. Next, we treat it as a wave and apply the wave equation to determine its wavelength. Finally, remember to convert your answer into nanometers, as meters will not receive full marks. One, find the correct transition. From part A, we know the photon's energy is 2.9 electron volts. We look at figure 21 to find two energy levels whose difference equals this value. Let's check the transition from n equals 5 to n equals 2. Delta E equals 13.1 electron volts minus 10.2 electron volts equals 2.9 electron volts. This matches our photon energy perfectly. 2. Determine the arrow direction. The question states that the hydrogen atom emits a photon. Emission means the electron is dropping from a higher energy level to a lower energy level, losing energy in the process. Therefore, the arrow must point downward. Pitfall. This is a simple 1-mark question, but the examiner's report notes that many students lost the mark due to careless errors with the arrow. The direction error. Since the atom emits light, the electron is losing energy and moving down. Drawing an upward arrow indicates absorption, which is incorrect. The missing arrowhead. Simply drawing a flat line between the two levels does not demonstrate a transition. A transition requires a clear vector, an arrowhead, showing the direction of the electron's movement. One, core concepts. Wave-particle duality. Identical diffraction patterns prove that electrons and X-rays share the same wavelength. Quantization. Atomic absorption and emission lines occur strictly because electrons transition between discrete, fixed energy levels. 2. The logic ladder strategy, backward mapping. Avoid simple formula plugging for complex multi-step calculations. Train students to map out a clear path in reverse before calculating. Accelerating voltage, V, kinetic energy, E, electron speed, V, wavelength, lambda. 3. Top 3 exam traps to highlight. The speed of light error. Never use c for electrons. Calculate their specific velocity dynamically from their de Broglie wavelength. Unit emissions. Standard formulas output wavelength in meters, m. Always perform the final conversion to nanometers, nm, when asked. Flawed transition diagrams. For photon emission, students must draw a straight vertical line bridging the exact energy levels, featuring a definitive downward arrowhead. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.